And now we have our second example. A tie rod and a pipe strut are used to support a 50 kilonewton load as shown. Tie rod AB has a cross-sectional area of 650 square millimeter and pipe strut BC has a 925 square millimeter cross-sectional area. So we have two members. So we have AB, which is our tie rod, and we have BC, which is our pipe strut. AB has a cross-sectional area of 650 square millimeter and BC has a cross-sectional area of 920 square millimeter. And both members has a modulus of elasticity of 200 gigapascal. So therefore, these are steel. Now, this load or this member here carries a support a 50 kilonewton load. So we have 50 kilonewton load at point B, and this is as shown. Okay, now our first question is determine the normal stress in tie rod AB and pipe strut BC. Then the second question is determine the lengthening and the shortening of tie rod AB and pipe strut BC. Then the third question is determine the horizontal and vertical components of the displacement of point B. And then the last question is to determine the angles through which members AB and BC rotate. So we try to solve our first question here, the normal stress in tie rod AB and pipe strut BC. But before that, let's compute for the axial forces in both members. So how are we going to compute the axial load in both members? So we apply joint method if you remember your truss analysis. So we cut at this section here. So if we cut at that section, then we have our internal, or we have our free body diagram here like this one. So we have at joint B, so we have our free body diagram. So we have at joint B, so we assume first the direction of the internal forces. So if we have our internal force or the axial force of segment AB like this one, that means that we assume it as tension. Okay, if we have our force acting away from the joint. But if we have a force acting towards the joint, that means it's compression. So this is our assumption. And let's say this one is our PAB and this one is our PBC. So again, these are only assumptions. So if we get a negative answer, that means we have wrong assumption. Okay, so we assume that our axial force for segment AB is tension, and the axial force for our BC or member BC is in compression. Okay, so our goal here is to compute for this value, but don't forget that we have a load at joint B which is 50 kilonewton. So how are we going to compute for the axial forces? So we apply equilibrium equation. So we sum up forces vertically and we sum up forces acting horizontally. You use either of the two first, but in this case, let's use summation of forces vertical, since we would come up with one unknown only. Since if you apply summation of forces horizontal, then you would have two unknowns, which is PAB and the horizontal component of BC. So let's compute first the value of PBC by summation of forces vertical, which is equal to 0. Upward forces are positive. Then we have two forces, okay? That is the vertical component of PBC. But how are we going to compute for the vertical component of PBC? So we compute first the angle in between, or the angle between PBC and 50 kilonewton. So how are you going to compute that one? Now take note, let's go back to the figure here. So we compute this angle. This is just let's say this is theta. Okay, now we can use tangent, which is tangent theta is equal to that is the opposite. Now the opposite of angle theta, this line here, which is 1.25, correct? We have 1.25 over the adjacent, and the adjacent is 1.15. Okay, so we have angle theta here, that is 47.386 degrees. Okay, that is our angle. So we have the angle at this point, which is 47.386 degrees. Okay, so we have summation of force vertical. We have the vertical component of axial load BBC, and that we know that we use cosine, correct, from your statics, cosine of 47.386 degrees. Since again, if you have PBC acting in this direction, so this is the vertical component. Let's say that is our PBC, the vertical component, and to the right side or the right direction, we have the PBC, the horizontal component. So to compute for PBCV, then we use cosine, since that's the adjacent of PBC, or that's the adjacent of our angle theta, correct? So I hope that you remember your statics on this. Then we also have the load 50 kilonewton, which is acting downward, so therefore that is negative. Okay, so we have negative 50 kilonewton. It's equal to 0. Okay, now we have positive vertical component of PBC since it is acting upward. So we have our PBC here, which is equal to 73.849 kilonewton. And then let's compute for the axial force PAB. So we have summation of forces horizontal is equal to 0. To the right, all the forces to the right are positive. Then we have here the horizontal component of load PBC, which we know we have PBC. Then we use sine, correct? Sine 47.386 degrees. That's positive since the horizontal component of PBC is going or is acting to the right direction. Now PAB here, since it is acting to the left direction, so therefore that is negative. PAB is equal to 0. Now we have the value of PBC already, which is 73.849 sine of 47.386 degrees minus PAB is equal to 0. So we have the value of axial load PAB, which is equal to 54.347. This one is in kilonewton. Okay, so these are the axial forces for our member. Now, since we got a positive answer for all the axial force, now PBCs, we have positive answer 73.849 kilonewton. So that means that we have correct assumption. And since we assume that PBC here is in compression, since this is acting towards the point or the joint, so therefore we have this PBC here, this is one is compression. And since our PAB here is positive, so we have correct assumption. And since we assume that our AB here is in tension, so therefore this one is in tension. So if we try to isolate every member, then we have this member AB here, which is 54.347 kilonewton, which is acting tension. And we also have for BC, which is 73.849 kilonewton, which is acting compression. And then we compute for the normal stress for every member we have here. Now let's begin with the normal stress of member AB, which we have the axial force AB over the area of member AB, which we have 54,347 over. Now the area of AB we have 650. This one is in millimeter squared, and the axial force is in Newton. So we have our normal stress for AB 83.611 megapascal. So this is our the normal stress of member AB, which is a tensile stress, correct? Since our AB since our axial force for AB is in tension. And then we have for normal stress of BC, we have the axial force PBC over the area of member BC. So we have here the axial force, which is 73,849. This one is in Newton, over the area, which is 925 square millimeter. So we have the stress of member BC here, which is equal to 79.837 megapascal. Since we have our axial force here that is in compression, so we have compressive stress. So this is our answer for the normal stress of member BC. Okay, then we have question letter B. We compute for the deformation of AB and BC. So we could have lengthening or shortening in member AB and BC. So we compute them individually. So the first one, we are going to compute for the deformation of member AB. And we have the formula again, that is the axial force AB times the length of AB over the area of AB times the modulus of elasticity of member AB. So we have here the deformation of AB is equal to the axial force of AB, that is 54,347 Newton. This in Newton. Our length of AB here, that is equal to 1,250 millimeters, over the cross-sectional area of AB, that is 650, that is in millimeters squared. The modulus of elasticity, that is, since we have steel materials, so they have 200 times 10 raised to the 3. The unit is in Newton per square millimeter. So our remaining unit here is in millimeters, since we could cancel out Newton and square millimeter. So the answer here, that is the deformation of AB, which equals to 0.523 millimeter. Since we have a tensile force for AB, then therefore it is expansion. Then we compute for the deformation BC, that is the axial force of BC, that is 73,849 Newton times the length of BC. And we all know that our length of BC is inclined, so we have to compute the length of BC by using Pythagorean theorem. So if this is the length BC, and we know that the horizontal distance is 1,250 or in millimeter, and the vertical distance here is equal to 1,150, we can compute the length by Pythagorean theorem. Then we say that the length BC is equal to the square root of 1,250 squared plus 1,150 squared. This gives us the length of BC equals to 1,698.529. So therefore, this one is 1,698.529 millimeter. So we have the length here, that is 1,698.529 mm, over the area of BC, that is 925 square millimeter, times the modulus of elasticity, that is 200 times 10 raised to the 3. And this gives us the value of the deformation of BC, that is 0.678 millimeter. Since our axial force here is compression, therefore we have the behavior of our BC, that is contraction. There is a shortening in the length of our member BC. So these are now the answer, the deformation of EB and the deformation of BC. Now question letter C asks for the horizontal and vertical displacement of B. Now after we apply a load of 50 kilonewton vertically at point B, the location of our B here has changed. Okay, so there will be a movement of joint B, but we do not know yet where would be the direction of B, or where would be the new position of B. Okay? So we can locate that point once we compute for the vertical and horizontal component of the displacement. Okay? The first thing we do here is to draw the deformation of AB and BC based on the deformation that we computed in problem B. We know that our AB here expands, correct? And it has expanded by 0.523 millimeter. So we draw. So this one is 0.523 millimeter. So this is the new position of B relative or with respect to the member AB. So let's say that is our B prime relative to AB. Okay? Now, for member BC, we know that our member contracts. So therefore, our position of B here would be in this position. Okay? So let's say this is B prime. That is the movement of B relative to that is BC. Okay? However, the final position of B will not be along these two axes. So our B here will move. Our B here will move here. So in order to determine the location of our joint B, we need to create a perpendicular projection of the axis AB and BC. So in this case, we can create a perpendicular to this one, to this axis that is, okay? So this is perpendicular. Please take note that I draw it in exaggerate manner so that we could internalize or we could understand the whole deformation diagram. After that, we draw a perpendicular projection of this axis, horizontal axis. So we draw a perpendicular. So therefore, this one is perpendicular. So our location of B here is where is the intersection of these two lines. So the intersection of this line and this line, in which the intersection is at this point. So we have here our new position of our B. Let's say that's our B prime. So to internalize the movement of B, so our B here moves along this line or this broken line here. Okay, so this is the movement of B. Since there is a movement of B here, so therefore we have a new position of the two members. So this green one, this green lines here, that is the new position of AB and CB due to the load 50 kilonewton. So our goal here is to compute for the horizontal and vertical displacement of B. So since our B new position is at this point, so it moves with a horizontal and vertical component. And our horizontal component here is this one. And our vertical component of the displacement is this one. But the length of deformation is this broken line here. Okay? This one. This is the deformation or the total deformation. So if we isolate this whole deformation diagram of our B, so we have here, we have this one in which this is 0.523, okay, and this is the movement of B relative to AB, and this one, since this is contraction, correct, it has a deformation value which is 0.678. So therefore this one is 0.678 millimeter. Okay, this is in millimeter. This is the new position relative to BC. But the final position of B is this one. Okay, so our goal here is to determine this vertical component and this horizontal component of the displacement. Now let's start with the horizontal component. Now we know that our horizontal component here is equal to the expansion of member AB. Okay, this length, this entire length here. And we know that value or the expansion of AB is equal to 0.523 millimeter. So this one is the horizontal component of the displacement of B. Now we compute for the vertical displacement. So this one. So how are we going to compute that? So we could use a lot of ways, no? The most important thing here is that we know, or we have the basic knowledge in trigonometry. So it is very important that you know how to compute for angles. So you could have used different method here, but I guess the most simplest form or simplest way for me is by creating a rectangle. So we could expand this one here. So we have created a rectangle. So our goal here is to compute for the vertical displacement, but we could have computed this one by summing up this length and this length. So let's say this is A and this one is B. So therefore, we could say that our vertical displacement is equal to A plus B. So our goal here is to compute for first A and B. Okay, so how are we going to compute this one? So by isolating this triangle here, okay, this triangle. So we have here, let's say this is X, okay, so we could have redraw that, isolate the triangle as this one, and this length is 0.678, this one is X, and this one is A. However, we need to compute for the angle here. And the angle at this point is just the angle at this point here. Okay, let's say this one is beta, and then we have our beta here is just the complementary angle of our angle theta, which is angle theta here is 47.386. So therefore, we have beta is equal to 90 minus theta, or we have beta is equal to 90 minus 47.386. So we have our angle beta, which is equal to 42.614 degrees. So therefore, our angle here is 42.614. Okay? So how are we going to compute for A? That is just by using sine. That is just 0.678. That is sine of 42.614. That is equal to A. So therefore, our A here is equal to 0.459 millimeters. Now, we need also to compute for X. So X there is equal to 0.678 cosine of 42.614. Then we have the value of X is equal to 0.499 millimeters. Okay, we are done with A. Now, let's compute for B. Okay? To compute for B, we need to determine the angle at this point. Okay, since we do not have other constant here, we don't have this length, we don't also have this length and this length. And we can compute this length here, this entire length, by summing up X and 0.523. Then we have 0.499 plus 0.523. This gives us 1.022 millimeters. So therefore, we can now finally compute for B, but first let's compute the angle here. And the angle here, that is just equal to the angle at this point. The angle at this point is 42.614, so therefore we have the angle here is 42.614 degrees. So how did I come up with 42.614? Take note, if this is 42.614, the angle at this point is the complementary angle, that is 47.361. And 47.361 here, then plus 90 degree angle, so the sum of this angle must be deducted from 180 degrees, correct? So therefore, the answer is 42.614 degrees. So we can now compute B here by using tangent. And that is just the tangent of 42.614 degrees is equal to the opposite 1.022 over the adjacent B, which is unknown. So B here is equal to 1.111 millimeters. So to compute for the vertical displacement, so we add A and B, that's equal to 0.459 plus 1.111 is equal to 1.57 millimeters. So this is the vertical displacement of joint B or the point B. Okay, so we have here 1.57 millimeter. Now to compute for the total deformation, so you just need to square root of 1.57 squared plus 0.523 squared. Pythagorean theorem. So our deformation of B, the total deformation, is equal to 1.655 millimeter. But since the problem only asks for the horizontal and vertical displacement, so our answer would be this one and this one. Okay, so these are the vertical and the horizontal displacement of B. Now we have the last problem, but still on problem number 2, we have the rotation of AB and BC. Since we know that our AB from this final or from this initial position, it has this final position, this one, this green one. So therefore, there is a rotation with respect to A. So let's say that's our theta AB. And the same as with our member BC, from this position, after the load P is applied, so it goes to this position. That is this green one. So therefore, this a rotation with respect to C, and let's say that's our theta member BC. Now, since our angle there is very small, we can say that our theta AB is basically equal to tangent theta AB, or just the tangent of the angle itself. Now we know that our tangent AB here, so if we look at the figure, this is a right triangle, this one. And then our tangent AB, that is just the vertical displacement over the length of AB. Okay, so if you try to redraw that one, this is the vertical displacement and it's the length AB. So we know that our vertical displacement, we have computed that one as 1.57 over the length of AB, that's the original length, which is 1,250, correct? This one is in millimeter, and this one is also in millimeter. Then you have the angle AB, that is equal to 1.256 times 10 raised to negative 3. Since we can cancel out millimeter and millimeter, then our unit here is in radian. So the rotation is clockwise. Now for the angle of BC, or the rotation of member BC, then that is just basically equal to tangent of the angle itself, and that gives us, or since tangent BC here is equal to, since this is 90 degrees at this point, so we could have this triangle. This one is theta BC. This is a 90 degrees. Okay, this is the length of BC. Now we do not know yet what is this length. Okay, let's say this is Z. So we have tangent theta BC is equal to Z opposite over the adjacent length BC. But our Z here can be computed by going back to this deformation diagram, and we know that this is Z. So how are we going to compute for Z? Using this 1.022 millimeter, and this B here is 1.111. So we could have our Z is equal to the square root of 1.022 squared plus 1.111 squared, and this gives us 1.5096 millimeter, or we could say that it's only 1.51 millimeter. Okay, so that is the value of Z. So therefore, our theta BC is 1.51 over the length BC, that is, we have computed the length BC, that is the square root of 1,250 squared plus 1,150 squared. So we have the angle BC, that is equal to 0.000889, and that is in radian. Then the rotation is clockwise. Okay, so these are the rotation of AB and the rotation of BC. But if you want to convert it into degree, you can multiply 180 degrees over pi radian. Okay, and this gives us 0.051 degrees. So imagine how very small the angle is. Okay, so it's almost zero. So these are angle rotation of AB, and this one is the rotation of BC in radian. That's it for the deformation of axially loaded member. In my next video, we will talk about deformation of indeterminate member or indeterminate structure. So thank you for listening. So I hope you like this video and subscribe.